Hello and welcome to this talk. I will present you the paper Learning Dependencies in Distributed Cloud Applications to Identify and Localize Anomalies. This is a presentation for the workshop on cloud intelligence, which is taking place in conjunction with the International Conference on Software Engineering 2021. This is the outline of the presentation. After a short introduction, I will introduce you to our approach. Subsequently, there will be our experiment design and evaluation, and eventually I will introduce you to our main findings and the conclusion. As for the introduction, it can be said that modern IT systems became increasingly complex over time, and this is why monitoring systems are often employed to collect metrics from such IT systems in order to gain valuable insights. Common methods that rely on the analysis of such metrics are, for instance, anomaly detection, anomaly classification, or root cause analysis, and especially the latter here focuses on understanding dependencies between systems and to also identify where specific faults are taking place. In this context, two questions naturally arise. How do systems depend on each other, and how can we localize faults in distributed systems? However, established methods can reach their limits in these vastly dynamic environments. For instance, if one uses manual rules, they need to be constantly adapted, and in certain cases, even expert knowledge is required. Or if KPI correlation graphs are used, they do often have a quadratic computational complexity because the metrics correlations are computed pairwise. So this is why in this work we investigate a data-driven and efficient alternative. We follow a three-steps approach, which is also illustrated on the right-hand side. The first step, for each system, we want to compute a vector representation of its local state. Second, we want to learn the dependencies between systems via graph convolution. And third, we want to improve the previously computed state representations using the neighborhood information. Let's have a closer look at the first step, which we call node feature extraction. First, we group all replicas of the same application service into so-called service groups. Later, members of the same service group will share the same node model and thus the same model weights, which will in turn decrease the number of trainable parameters. Our node feature extraction can be split into two parts. First, we want to extract features from the system KPIs that we have recorded using convolution. And second, we want to compute compact node representations using global pooling, so that it's invariant to the number of KPIs. On this slide, the node feature extraction is summarized. As you can see, we do have multiple groups and also multiple replicas assigned to each group. For each group, we do have a node model where we do have the convolution step, which is composed of a convolution layer with different kernel sizes, a nonlinear activation function, a max pooling to discard weak neuron activities, and also a normalization step. And also for the transformation, there is a linear transformation to map to a desired hidden model dimensionality, and finally a global max pooling to condense all metrics to a single vector, which is then the respective state representation of a system. After computing a state representation for each system, we can now look into the second step, which is the dependency model. What we essentially want here is to fabricate edges between nodes. For this, we assign a tag to each edge, then we encode the tag to derive a vector, and then we use this derived edge attribute vector and the previously computed node features, aka state representations, to learn the dependencies between systems. On the right-hand side, you can see a table of edge types that we have defined. While the very first three are self-explanatory, we use a unique group tag for each unique group, and we use a unique dependency edge tag for each unique directed dependency between two systems. And here you can see examples for such tags. For instance, the identity tag is just the word identity, but for a tag for group 1, it's group 1 as a tag, and then we have a dependency from group 1 to group 2, and then this is also a unique tag. So eventually this will give us a number of tags, and then we can use these tags to encode them via one-hot encoding. So for instance, if we have an edge from I to J, and the dependency is group 1 because both systems are part of the same group, then we can use the encoded version, in this example 0001, this vector, and this is now the edge attribute vector of this specific edge. After obtaining the edge attribute vectors, we can now finally proceed to derive and compute the actual edge weights between two systems. For this, we introduce a transformation function f, which takes into account for one specific edge the state representations of the connected systems and the respective edge attribute vector, and will output a scalar value. Of course, since multiple edges are associated with one source or root node, we need to employ a posterior softmax calculation so that the sum of all edge weights associated with a specific node sums up to 1. The learnable transformation function f will eventually give us the connectivity matrix of our graph, which we can then exploit to improve our previously computed state representations. This graphic summarizes our approach. So we can either go with our later used as a baseline approach of just taking the state representations, using a fine linear layer and a softmax layer, and then using the computed probability distribution to detect and identify the predicted anomaly. Or we use actively graph convolution, exploit the neighborhood, enrich our local state representation, add this information via a residual connection to the state representation, and then proceed and calculate the probability distribution. In order to verify if our method is beneficial at all, we design an artificial experiment. We simulate two cloud applications hosted within virtual machines of a cloud system, and we base this on the deployment layouts of two popular cloud applications, which eventually results in 51 system components, both host and actual virtual machines. We then synthetically inject anomalies. When it comes to the KPIs of these system components, we draw samples from differently parameterized distributions, and we go with 10 KPIs for each system component. If there is an anomaly is injected into a randomly selected KPI, so all other KPIs are still behaving as normal. And also, there's no temporal overlapping of anomaly injections. So at any point in time, there's only one main anomaly in one of the systems. In order to demonstrate that incorporating neighborhood information is in fact useful, we're designing multiple scenarios. The first one is the local scenario, which has a probability of arising of 70%. In this scenario, an anomaly is injected into a target system, whereas all other systems are behaving normal. Normal means that the values we are drawing from the normal distributions have a standard deviation of 0.2, whereas the anomaly or the values that represent the anomalies are drawn from a normal distribution with a standard deviation of either 0.1 for the anomaly 1 or 0.3 for anomaly 2, as we are also interested in looking into multiple anomaly types. The second scenario is the neighborhood scenario, which has a 20% probability of arising. In this scenario, the target system shows miscellaneous signs. So the values that we are drawing from the normal distribution are closer to the values that represent normal behavior than the actual anomaly. However, the neighboring nodes are experiencing the original anomaly. So the test here is, if our own local state is not clear to us, can we incorporate information from our neighborhood to decide if an anomaly is happening or not? Finally, there's the adversary scenario, which has a probability of arising of 10%. In this scenario, a target node experiences a certain anomaly, but the neighboring nodes or neighboring systems are experiencing a different anomaly. The test here is to show or to investigate if when there is enough knowledge on the local state to not rely on information from the neighborhood, because in this example it would be confusing and not helpful. For the evaluation, we first assign IDs to the sequentially injected anomalies. It is worth mentioning that each anomaly is injected 5 times into each application service. So then later, when we use leave one group out cross-validation, we arrive at 5 groups or 5 splits into training data and validation data. The normalization of the synthetic KPIs is then based on the training data. We also extract subseries of the synthetic multivariate time series, aka KPIs, with a window width of 20 and a stride of 20. We do so to operate on fixed size input data. For the model, we use different convolution kernels. We have one kernel size for the max pooling operation, and also we don't use any biases for linear layers and convolution layers. More details regarding the configuration and the training can be found in the paper. This slide shows the results for the detection of specific anomaly types. We report the results in terms of the metrics F1 score, precision, and recall. It can be seen that using neighborhood information in graph convolution, we can increase F1 score, precision, and recall for all anomaly types. Also, it can be observed that the variance is much more stable. The same applies to the localization capabilities of our approach. Using graph convolution and neighborhood information, we are able to achieve better localization results, even for small values of k. This is even the case when we do localization of specific anomaly types, as depicted on the right-hand side. Finally, we want to assess how good we were able to localize anomalies that we have injected into our target nodes. Not surprisingly, for the local and adversary scenario, the changes are not too big. However, for the neighborhood scenario, it definitely pays off to incorporate neighborhood information via graph convolution, as you can determine anomalies even if your own local state is miscellaneous. In conclusion, we have shown a simple method for computing state representations of systems. This method is invariant to the number of KPIs that were initially recorded. Also, we have shown a way of propagating information via graph convolution for better identification and localization of anomalies. Our very first results verify the potential of our method, and so of course now the next steps are, okay, what can we do? And can we also consider the indirect neighborhood, because so far we have only incorporated the direct neighborhood. And of course, evaluation with data from real-world deployments to actually verify how our method behaves and scales in real life. Thank you for listening, and I'm now happy to answer any of your questions.